Freq Physics Basic Acoustics Lesson 2. An earful of physics. Sound travels into the ear as a wave and is then converted to electrical signals to be sent to the brain. The volume of a sound varies from person to person as well as from species to species. The volume is the perceived loudness. This varies due to the sound being defined by frequency among other properties. The human ear can hear frequencies up to 23,000 Hz. However, a dog can hear up to 45,000 Hz. So what's loud to a dog may not even be audible to a human. In this lesson we will explore the mechanics of the human ear and how it interprets sound. Enjoy.
So our discussion for today is the ear and how you hear, as you are right now through your computer, listening to my voice, and we'd like to talk about how that works. The last time we met we talked about the eye. So we have our slide here. I gave you this diagram yesterday or recently, and I'd like to go through the parts of it. First of all, the anatomy of the ear. Number one we have is called the pinna. The pinna is the outer part of the ear, but I write the outer part of the ear, but it's more important than that actually. It acts, if you feel your pinna right now, if you feel the kind of the shape of it, you got these ridges and curls, and maybe you've wondered why in the world we have such a thing. Your dog has floppy ears maybe, or pointy ears. Your cat kind of the same. They don't have the furrows and they don't have the ridges. And we're pretty sure the reason for that is to make a funnel for sound. If you think of your cat especially, or even a dog that has pointed up ears, like maybe a German Shepherd, they can swivel their ears in the direction of the sound they hear. You, well, unless you have a special talent, I really can't do that. You may be able to wiggle your ears up and down or something funny like that, but you really can't turn them. Well, if you see like ears are kind of tipped forward, and if you trace around if you trace from the outside of your ear, trace the ridges, you'll find that they funnel right to the inside of your ear. And if you have somebody talk to you and cup your hand behind your ear, you'll notice, or pull your pinna out and then pin it back against your head, you'll notice the difference in volume. It's a very good collection for sound. It also makes a very good place to hang jewelry from for some people. The next part, moving inward, what I have written is number 5 here. Let's see if that color shows up better. Yeah. The number 5 is the ear canal. The ear canal is like the tube of the funnel, funneling sound into the inner part of your ear. So if you're thinking of the pinna and the ear canal together as a funnel, that's what you have. Now what you have in the ear canal is a yellow substance known as earwax, and you've lived with earwax your whole life. You may clean out your ears periodically, hopefully, because that wax will build up, and if it builds up enough, it could clog your ear canal. So you need to clean out the wax periodically. We're not exactly sure why earwax exists. We think maybe it's catching stuff that falls into your ear, but we're not exactly sure. It's made from modified sweat glands. So they produce, obviously, this fatty substance, which we call wax. It is yellowish. Interestingly, different races of people have different kinds of earwax, but for like different textures of earwax, I guess, dry and crumbly versus moist and kind of like yellowy. Anyway, earwax can build up in here, and you probably go out and buy Q-tips to clean that out, and that's really kind of a bad idea. The thing with a Q-tip is a Q-tip is pretty much the exact same size as the ear canal. So as you shove the Q-tip back into your ear, you pack a little bit of wax back here against your eardrum, a little bit at a time, a little bit at a time. And what you could end up doing is making like a wax rock that is against your eardrum here that prevents sound from getting through. My brother had this, interestingly. We went to the ear doctor together. He was having a hard time hearing, and I had tubes stuck in my ears. They weren't coming out. And I still remember him getting them putting some solution in his ear and then rinsing it out, and this giant rock of wax kind of fell out of his ear. It was like hard as a rock. They like picked it out of his ear, and he instantly could hear better. So you might ask, what do I clean my ear canal with? Because that's what he asked. He's like, well, how do I clean out my ears? I'm not supposed to use a Q-tip. And they're like, well, you take a little hydrogen peroxide, and you can try this at home. Take a little hydrogen peroxide and dump it in your ear canal, and it makes a very interesting sound. And then after a little while, you take like one of those baby nose sucker things, and you suck out your earwax, and you've cleaned out your ear just very nicely. Number 6 here then, already the aforementioned eardrum. Eardrum is like a very thin, very thin membrane, kind of like a skin that covers the opening to the ear canal, that covers the end opening to the ear canal, the end of the funnel, if you will. And as sound hits it, the eardrum vibrates. And it's possible to, and that's really pretty much all it does as far as we can tell, is that when the sound hits it, it vibrates. And it's because it's such a thin membrane, it can be burst, it can break, it can crack. And so if it bursts, if you think about hitting a drum, if you put a hole in that drum, it doesn't vibrate as well. Same thing with popping your eardrum. It's possible to pop it, and but it also will heal. Sometimes they have to do surgery, maybe stitch it up a little bit to help it to heal. The main reason you pop your eardrum, if you don't stick something into your ear, which doesn't sound like a good idea anyway, is differences in pressure, which we'll cover in a second. But anyway, so as sound waves travel in, they make the eardrum vibrate. And again, a brief little segue into sound waves. Remember that when we talked about light, light travels in waves, sound travels in waves. And we measure wavelength. We also call that frequency when we talk about sound. And it also refers to pitch when we talk about sound. So, is a high-pitched noise, which means it has a high frequency. There are many waves passing in a second, whereas is a low pitch, which means you have few waves, a lower frequency, fewer waves passing at the same at a point. Now, amplitude, if I talk very quietly in a low voice, you have low amplitude and low frequency. And very loud and high voice is a higher frequency and higher amplitude of wave. And so your eardrum vibrates more and harder as sound hits it, which if you think about this, if you get a loud enough noise, you could actually burst your eardrum. Number 2, 3, 2, 3, and 4 are the hammer, anvil, and stirrup, also known as the Malleus if you use the Latinized form, incus and stapes. These are the 3 smallest bones in your body. You may have learned that factoid once upon a time when you were younger. The Malleus, incus, and stapes, which as the eardrum vibrates, they transmit, as far as we can tell, their whole function is to transmit the vibrations from the eardrum into the sensory organ of the ear, which is back here. We haven't really figured out if there's any other thing for those. And they do it very, very well in almost everybody. So part number 7, down here, which really isn't for hearing per se, is the eustachian tube. The eustachian tube connects your inside of your ear here to your throat. So just below your chin, just below the point of your mandible down here, coming out from your ear, is the eustachian tube. And the point of the eustachian tube is to equalize pressure. So if you think about this, if you go up a mountain, or maybe you've closed the windows in your car and you feel it in your ears, what you're feeling is the change in air pressure happening out here compared to the air behind your eardrum. So This is kind of hard to explain without you being able to see me, but as the eardrum, as air pressure is higher out here and lower in here, that will create a general pressure against your eardrum, which prevents it from vibrating. And maybe you pop your ears, and that pop you're hearing is when the pressure is suddenly equalized, generally by air coming out your eustachian tube. This is why if you fly, you chew gum, or you yawn, or you do something like that to straighten out your eustachian tube to allow, let's pretend that this is higher air pressure in here, which is true if you've gone up a mountain or up in an airplane, that this air has to come out to equalize the pressure. So the eardrum is getting pushed out from behind, and then the pop you hear is it snapping back. And when it snaps back, transmits a popping sound through your sensory organs, and you don't feel this, but the air comes out in your neck. Many young children have this eustachian tube, because they're so young, is curved. Instead of coming smoothly out to your neck, it's kind of curved like this. And this becomes a breeding ground for bacteria, which is why many children, young children, probably many of you, have a lot of ear infections when they're young, because the bacteria get trapped in this tube, and then they make their way up into the middle ear, and you get what's called otitis media, which is a middle ear infection, extremely common in young children. Sometimes, if you have otitis media, to help drain the bacteria out of your ear, because they're not draining this way, they put a little tube, so that here's your eardrum, they will put a tube through your eardrum, and then when you're sleeping at night, if you ever had one of these, you'll notice in the morning you would have a little puddle of pus on your pillow maybe, because your ear infection has been draining out your ear canal. And it's a very common procedure. Generally, the tubes are tapered, so as the eardrum grows back, the tube gets slowly and slowly and slowly moved out until it just falls out on its own. We can, if you have more questions about that, we can talk about that when I'm in class. Number 9 is the auditory nerve, and it brings the message to the brain. What we have to talk about is what actually the message is. And that message comes from number 10, this snail-shaped organ here called the cochlea. The other thing you see on this slide are these things up here, which I'm going to label number 12. These guys, the semicircular canals, which actually, as far as we can tell, have no use in hearing at all, but they are used for your sense of balance. So we'll be talking about the semicircular canals a little bit later on. So what I'm going to tell you here is our best theory on how we hear. We're not exactly sure, but okay, so you don't have to write all this, right? We just talked about this part a minute ago. The cochlea basically converts the vibrations of sound waves of the hammer, anvil, and stirrup to nerve impulses using tiny little hair cells that occur inside of there. And we're going to talk about hair cells again. We talk about your sense of balance. But along inside the cochlea here, this spiral-shaped organ, are hair cells that will convert the vibrations of sound to nerve impulses. So here's our best guess on how this works. If you stretch out the cochlea, so you unwind the snail. Okay, remember it's curled up. If you unwind it, at this end, you have the stirrup attached. And then you have this like middle part. And then at this end is the other side of the cochlea. And let me just go back a slide to show you this. This is called the round window right here. So you have the oval window here where the stirrup is attached, and the round window at the other end. So what I've done is I've unwound the snail shape thing. all along the middle of this. So this is the upper part here, and this is the lower part. So over here, we have the upper part and the lower part, and this is what's in the middle. So you see that along in the middle is something called the organ of Corti. And what we think happens is as the stirrup bangs on the oval window, it sets up waves. What's in here is a liquid. Let's call it water. It's probably not water, but it's a liquid, and as you hit one side of the liquid, it sloshes, and it sloshes, its vibrations happen in a certain rhythm, right? Like if you took your water bottle, you can squeeze it in a certain rhythm and set up vibrations. And what happens is those vibrations of liquid move these hair cells. They move these hair cells here in the organ of Corti. Those hair cells vibrate on the tectorial membrane, and those hair cells are connected to the auditory nerve. So the auditory nerve takes the messages from the hair cell. As the hair cells are vibrated, that depolarizes them, sending a message down the auditory nerve. And so in hearing, what we think happens is you take la, that these, when I make that sound, these are taking the organ of Corti, apologize. Shoot. The organ of Corti, let me go back a minute to it. The organ of Corti, quote, feels, these hair cells feel those long vibrations. And those hair cells vibrate along with, so if you have a, struggling here, you have a, they'll vibrate slowly on a soft sound. The waves will only go a little ways. On a louder sound, the waves will go farther along, maybe all the way to the end. The the round window here is here to relieve pressure, and that's how you hear. This is our best hypothesis on hearing. Now, how we understand words and how we understand, all that stuff as opposed to song, music, as opposed to just background noise, well, that's in the brain, and that's another area where we're not exactly sure of how everything works. But that, overall, is the ear.
We hope you enjoyed this video, and for more lessons and videos go to freqphysics.com.